Hi, I'm Charithea Charalambous, and I'm a postdoctoral research associate in the Research Center for Carbon Solutions of Heriot-Watt University. It's with a great pleasure that I present our work today on CO2 recovery from ultra-dilute streams, bridging a novel temperature vacuum swing adsorption model with material screening. I will start this presentation with the introduction to the PrISMa project founded through the European ACT program. Then I will introduce the aim and objectives of this study. Then the description of the temperature vacuum swing adsorption model follows, including model validation and results from 2 case studies. Then I will present results from material screening with a particular focus on CO2 removal from dilute streams. And finally, I will close the presentation with the main findings and future work. The PrISMa project aims to accelerate the transition of energy in industrial sectors to a low-carbon economy by developing a technology platform to tailor-make cost-efficient carbon capture solutions for a range of different CO2 sources and CO2 destinations. This technology platform then takes into consideration the different CO2 sources and sinks, and by bridging molecular simulations with process modeling, it screens thousands of adsorbent structures to identify the most promising adsorbents for each application. The ultimate task of this project is to integrate a techno-economic tool for material screening. After these steps, the most promising adsorbents are synthesized, characterized, and the results are validated against the predicted ones, with the ultimate task to identify the optimal adsorbent for each application in the matrix. The project has already been presented by the project leader, Susana Garcia, in the first CO2 capture by adsorption session. For more information, please have a look at Garcia's pre-recorded presentation. Today, I will focus on the first part of the platform, which is highlighted inside the blue rectangle here. With this platform, we aim to build a tool to run meta-organic frameworks for particular applications. Here, we extend the work of our group by bridging molecular simulations with process modeling to screen thousands of materials for adsorption applications. This work starts with the development of an automated interactive infrastructure and database AIChE for computational science. This platform takes data of thousands of adsorbents, and through data refinement, geometry characterization, and optimization, it computes adsorption properties for thousands of adsorbents. Finally, for different applications, AIChE ranks these adsorbents based on selected adsorption properties. Here we extend this work by integrating adsorption properties and application characteristics into process modeling and optimization for ranking these adsorbents based on selected process metrics. We use the temperature vacuum swing adsorption process for a screening. It starts with the adsorption step, during which the feed stream, in this case CO2 and nitrogen, is fed into the column until saturation, and the less adsorbed component leaves the column from the other end. The second stage is a quick vacuum step, during which the column is open to vacuum for a short time until a significant amount of the less adsorbed compound leaves the column. Next is the heating step, which is performed with the bed open on one side and under vacuum pressure for collecting the CO2 product. Then the bed is repressurized and cooled down to adsorption temperature. After this step, a cycle is completed and the column is back to the adsorption stage. In our simulations, we always start from stage 2, as we know the initial conditions of that step. Those are equal to the final conditions of the bed after saturation. The assumptions we consider for the development of the process are given here. It's important to mention that the quick vacuum step is modeled assuming a frozen adsorbed phase, which means that we assume that nothing leaves the adsorbed phase during stage 2. Also, heating and cooling steps are modeled in discretized temperature steps. It's worth mentioning here that this is the first time that the temperature vacuum swing adsorption model has been used for material screening. For assessing the performance of the process, we consider the CO2 removal from spacecraft cabins application, and the input parameters are provided here. CO2 and nitrogen pure component adsorption data on 13 negs are taken from Fermahini and al. And we use extended dual cell Langmuir for co-adsorption. Here you can see the purity, recovery, the working capacity improved by considering a temperature vacuum swing adsorption process instead of a standard TSA process, and by decreasing the vacuum pump level from 0.2 bar to 0.1 bar for a range of desorption temperatures from 80 to 215 degrees C. The TSA model has been validated, and the results are provided in Appendix A of this presentation. Next, I should mention also that we also calculate the vacuum pump duty for the TVSA process, but the results are not included in this presentation. Now, the TVSA model has been validated against an in-house detailed model, and the results are presented here. We also provide the results from the model validation in appendixes. You can see here that at higher regeneration temperatures, the models are in a good agreement. However, the thermodynamic model over-predicts the process performance. Although these results are expected, since no heat transfer and kinetic dispersion and kinetic effects are introduced in the thermodynamic model. So we demonstrate that the dilute streams, for dilute streams, the vacuum improves the process performance. For now, I will refer to this application as CRSC. Similar trends are observed for CO2 removal from pulverized coal power plants. From now on, I will refer to this application as PCCS. So two main conclusions here are so far are the intermediate vacuum step, the quick vacuum step, and regeneration under vacuum improves purity, recovery, working capacity, and specific thermal energy. However, the vacuum pump is required, and this comes with an extra energy and cost. And secondly, the higher the dilution of the feed stream, the lower the process performance. Now, after integrating molecular simulations with process modeling, here are our preliminary results from ranking the process performance using around 30 structures. The two plots on the left-hand side present the results from the CRSC case for heating at 100 and 200 degrees C, and the one on the right-hand side, the PCCS case for heating at 200 degrees C. The materials that perform better are the ones listed at the top of the slide, with the best performing one to be the NOD 300. The process performance, as you can see, dropped significantly using the structures. One of these structures is 13X, and it's highlighted within the blue circle here. As we shown in previous slide, 13X resulted at much higher purities for the case of dilute streams. Therefore, we took a step back to look at the isotherm data to understand why this happens. In this slide, you can see our CO2 pure component data, isotherm data at 10 degrees C, noted here as 13X EPFL, compared against a set of computational data provided by Fermahini and al. And denoted as 13X as Sarkisov, and set of experimental data provided by Jones et al. Denoted as 13X Mesotti. If we look closer now at Henry's region on the logarithmic scale, we see that the CO2 loading at the low pressure range is much lower in our case, and to be more specific, the CO2 uptake is predicted to be half at feed concentrations and adsorption conditions in comparison to the other two data sets. Then we use these three data sets in our process models to compare the prediction of the process. And as you can see, the performance is worsened and is shown different for each of the data sets. The same implies for both CRSC and PCCS cases. This can be explained by the differences between pure component data and model used for predicting co-adsorption. The extended dual cell language was used with the data from PharmaHini, extended SIPs with the data obtained from JOS and JOS, and IAST with our data. Other differences are in the material properties and process characteristics. However, this work needs further investigation to understand which approach gives us more realistic predictions. Then we look into co-adsorption of co-adsorption models, and we plotted the binary isotherms and compared the CO2 loadings for two cases, adsorption at 10 degrees C and 0.004% CO2 in the binary mixture, and 100 degrees C and 14.3% CO2 in the mixture. Here we have we used three different methods to predict co-adsorption. One is PharmaHini's dual cell language parameters with extended dual cell language, our computational data with extended dual cell language, and the same computational data with ideal adsorption theory. As you can see, the results are pretty different for all three cases, even though for two cases we use the same pure component isotherm data, and this difference reveals a challenge when it comes to which method the database to use. Now, the main results here are that the material ranking results are affected by the case study, the adsorption process, the process specifications, assumptions, the model complexity, the material properties. And of course, the performance is extremely dependent on the isotherm data. So we need to be careful when selecting the isotherm data and which method to use for predicting co-adsorption. Next steps are to build an integrated techno-economic tool for material screening, add more processes and process complexity, and improve the process metrics, generate more material data for screening, and add a matrix of CO2 sources and CO2 sinks destinations. Finally, I would like to thank you all for your time to listen to this talk, and thank, of course, our funders. Thank you.